Now we'll discuss the next application of Gauss's law, that is electric field due to an uniformly charged infinite plane sheet. Here is a plane sheet which is uniformly charged. Let the surface charge density be sigma, that is charge per unit length area is sigma. Due to this plane sheet, there will be electric field coming perpendicular to the surface towards right as well as towards left. Electric field intensity in this direction as well as in this direction. Now, we are going to take a Gaussian surface in the shape of a cylinder. This is a imaginary Gaussian surface in the shape of a cylinder, each flat surface having area A. Our aim is to find the intensity of electric field at this point. Let it be E. You'll have E in this direction also. Now, this imaginary Gaussian surface is cutting through this plane sheet over this area. It is again area A. Is that clear? Now, what will be the total flux over this Gaussian surface? Across these two flat surfaces, the intensity of electric field and area vector, let me call this area as ds1. This one ds2. This flat surface and this flat surface. And this curved surface. I have taken small element here, okay, of area ds1 and ds2. Similarly, I am taking a surface on this flat surface ds1 and ds2, and on this curved surface I am taking ds3, a small element. Okay. Now, what will be the total flux over this entire Gaussian surface? Surface integral E dot ds will be closed surface integral, that means entire closed surface. Surface integral E dot ds1, that is over this surface, plus surface integral E dot ds2, that is over this surface, plus surface integral E dot ds3, that is over this curved surface. The angle between E and ds1 is 0 here, 0 here also, but here it is 90 degree. Therefore, what is E dot ds1? It will be surface integral E ds1 cos 0 plus surface integral E ds2 cos 0 plus surface integral E ds3 cos 90. We know that cos 90 is 0 and cos 0 is 1. Now, it's continuing it here. Surface integral E ds1. Surface integral E ds1 ds1 plus surface integral E ds2, because cos 0 is 1, plus 0 cos 90 is 0. Now what is, E is constant over this entire surface, because this surface, any point is equidistant, same distance from this charge sheet. For this I can write as E surface integral ds1 plus E surface integral ds2. If I add up summation of ds1 over this surface, this surface has got area A. What do I get? EA, because in surface integral ds1 is A. Same, this is also EA. What is this? 2EA. So what have I got here? Surface integral, it is the total flux over this entire Gaussian surface. How much is it? 2EA. Now, what by Gauss's law, what should be this total flux equal to? It should be equal to the total charge enclosed by this Gaussian surface into and upon epsilon naught. But phi E is equal to Q upon epsilon naught. But what is Q? What is the charge enclosed by this Gaussian surface? It is a charge in this on this area, which is also A, multiplied by surface charge density. Therefore, this is going to be sigma A. Now, substituting this value of phi E and this value of Q in this equation, what do we get here? 2EA is equal to 2EA, which is phi, is equal to, what is Q? Sigma A upon epsilon naught. What gets cancelled here? A gets cancelled. What is E? E is equal to sigma by 2 epsilon naught. This gives you the intensity of electric field near a uniformly charged infinite plane sheet. Is an important derivation. Application of Gauss's law. Now let us take other cases. Remember this, E is equal to sigma upon 2 epsilon. Now we want to find intensity of electric field due to two plane sheets of charges. Here, two parallel plane sheets of charges. Here is one sheet, here is another sheet, both parallel to each other. Let me call this plate A, or sheet A and sheet B. Let us say this is positively charged. Both are, let me say, the surface charge density of the first one is sigma A and this one is sigma B. Both are positive. Okay, two plane sheets of charges, infinite plane sheets of charges, uniformly charged, having this one having surface charge density sigma A, this one sigma B. Our aim is to find intensity of electric field in region 1, region 2 and region 3. We take a convention, any direction towards right is positive and towards left is negative. Now at region 1, intensity of electric field due to this plate A will be towards left, because electric field perpendicular to the plate or sheet, and due to B also will be towards left. And left direction I am taking as negative. What is that? Minus sigma 1 upon 2 epsilon naught, because due to one plate it is sigma by 2 epsilon naught. Therefore sigma 1 by sigma A I have taken. Okay, here minus due to the second one also towards left, electric field from this positive will be towards this direction. Sigma B by 2 epsilon naught. What is this? Minus sigma A plus sigma B upon 2 epsilon naught. This is the electric field intensity in region 1 due to these two plates. What about region 2? Here, the intensity of electric field due to plate A. Here let me show. EA was towards left, EB was also towards left. Now here, EA will be towards right, EB will be towards left. Therefore, EA, what is that? Sigma A by 2 epsilon naught. EB being towards left will be negative direction, sigma B by 2 epsilon naught, which will be sigma A minus sigma B upon 2 epsilon naught. This is in region 2. Now, what about region 3 here? In region 3, due to this plate, field will be towards right, EA. Due to the second plate also, it will be towards right. Both towards right. That means both positive. So, region 3, what is EA? Sigma A upon 2 epsilon naught plus, this is plus because it is towards right. Due to B also it is plus because it is towards right. Sigma B by 2 epsilon naught, which will be sigma A plus sigma B upon 2 epsilon naught. Okay? Now, we got E1, region 1, region 2, region 3, formula for intensity of electric field. Now let us take a case in which plate A is positively charged with surface charge density sigma, and plate B is negatively charged with surface charge density minus sigma. Magnitude of sigma is same in both. So, what will happen to E1, E2 and E3? Now, sigma A is plus sigma, sigma B is minus sigma. Then what happens to E in region 1? Minus of sigma minus sigma upon 2 epsilon naught, which is 0. If electric field on the left hand side, region 1 is 0. If the two plates are, one is positive and the other is negative, having equal surface charge density. Now, what about region 2? In region 2, this is the formula. What is that? Sigma minus of minus sigma upon 2 epsilon naught. That is sigma plus sigma upon 2 epsilon naught. That is 2 sigma by 2 epsilon naught. How much is that? Sigma by epsilon naught. This is in region 2. That means between the two plates. Now, in the third region, region 3, to the right side of the system of two plates, what will it be? E3. Here, instead of sigma A, I'm going to put plus sigma. Here, I'm going to put minus sigma. What do we get? Sigma minus sigma upon 2 epsilon naught, which is equal to 0. That means if you have two equally charged plates, infinite plane sheets of charge, there will be no electric field on either sides, but you will have an electric field of intensity sigma by epsilon naught between the two plates, in the region between the two plates. Okay? Now, let us go ahead. So you have learnt that if the two plates this is having plus sigma, this is having minus sigma, here electric field intensity is 0, here also it is 0, and from the positive to negative plate you have a uniform electric field given by sigma upon epsilon naught, where sigma is the surface charge density of each plate. Now, next application of Gauss's law is to find electric field intensity due to a uniformly charged spherical shell. This is a shell of radius r. It has got a charge q which is uniformly distributed over the surface. What will be if the surface charge density of this sphere is sigma, that is charge per unit area is sigma, then this q will be surface area of the sphere 4 pi r squared into sigma. Okay. Now we want to find intensity of electric field in three different regions. One outside the sphere. Let us take a point P here, which is at a distance, let us say, small r from the center. We want to find intensity of electric field here, E. We're going to derive it using Gauss's law. Imagine a Gaussian surface of radius small r. Now, what will be the total flux over this surface? Over this imaginary Gaussian surface of radius small r. Small r is the radius of this imaginary surface. The flux is going to be surface integral E dot ds. I'm taking a small surface area ds here. Surface integral E dot ds. You know the value of E will be same at any point on the surface because it is at the same distance r from the center. Therefore, and the angle between ds and E is 0. Therefore, surface integral E ds cos 0 is 1, and E being same, I can take E outside the integral E integral ds. What is integral ds? It is going to be E into, if I add up all the ds for this curve, this spherical surface, you get 4 pi r squared, surface area of the sphere. I got phi. But by Gauss's law, what should this phi be equal to? It should be q upon epsilon naught. Therefore, phi, which is this value, E into 4 pi r squared, should be equal to q by epsilon naught. I want expression for E. Now, what is E? Take 4 pi r squared towards the right side. E will be equal to 1 by 4 pi epsilon naught q upon r squared, which is the same formula for intensity of electric field at a distance r from a point charge q. That means for any point outside the spherical shell, the entire charge on the spherical shell, can be assumed to be concentrated at its center. Okay? This is outside E1. Now I want on the surface, what will be the intensity of electric field on the surface of the spherical shell? So take a Gaussian surface along the surface of the charged spherical shell. What will be the flux over that surface? Let me say E2. Here you can show the same way. It is equal to 4 pi r squared E2 on the surface. Okay, what will be the charge enclosed? It will be Q, and what is that Q equal to? 4 pi capital R squared sigma by Gauss's law. What is phi E? It is Q by epsilon naught. What is this? 4 pi R squared E2 phi E into Q. What is Q? 4 pi capital R squared sigma upon epsilon naught. What gets cancelled here? 4 pi R squared, 4 pi R squared. Therefore, what will be intensity of electric field on the surface of this charged spherical shell? It will be sigma by epsilon naught on the charge, on the surface. Now, one more point I have to take. That means a point lying inside the spherical shell. Let me take a point here at a distance r dash, which is smaller than capital R. Form a Gaussian surface here. Let electric field intensity here be E3. Then, what will be the flux over that Gaussian surface of radius r dash phi E? It will be, we can show that it is 4 pi r dash squared E3. What is the charge enclosed by this Gaussian surface? Is there any charge inside this Gaussian surface? No, the charge is 0 enclosed. But phi E, you know, is equal to Q upon epsilon naught. That means 4 pi r dash squared E3 is equal to 0 upon epsilon naught. It is 0. That means E3 is 0. There is no electric field inside the charged spherical shell. And on the surface it was sigma by epsilon naught. And outside it was 1 by 4 pi epsilon naught Q by R squared. So, if you plot a graph between the electric field intensity on y-axis and distance from center of the sphere on x-axis, this is the center. You know, this sphere has got maximum, its radius is r. You can imagine the sphere. Inside the sphere, the electric field intensity was 0. It was maximum on the surface, that means at the distance r. And what was that value? Equal to inside E was 0, and on the surface, what was it? It is 1 by 4 pi epsilon naught Q upon capital R squared. You remember Q was 4 pi capital R squared sigma. Now, as you go out away from the surface, we found intensity of electric field was inversely proportional to R squared. So you get a graph like this. This is on the surface. This was E3, E2. What was E1? It was found to be inversely proportional to R squared.